Let me introduce Carl Vondrick. Professor Vondrick is an assistant professor of computer science at Columbia University, where he directs a research group on computer vision and machine learning. Prior to that, he was a research scientist at Google, and he received his PhD from MIT in 2017. His research got funded by NSF, DARPA, Amazon, Toyota, and he received several awards. Some of them are the NSF Career Award, Toyota Young Faculty Award, and an Amazon Research Award. So yeah, thank you, Carl, for coming. We are very happy to have you here and to hear about visual recognition by reading. It's a great, exciting title.
Thanks so much, Adam, and thanks so much for inviting me. And hopefully everyone can hear me in person. So yeah, I'm going to talk about some ways of work that we've been exploring about what we call visual recognition by reading. And this is some work we just recently did, so I'm pretty excited to share it. And so, one thing my group has been getting very curious about is just how good these language models are. You've probably all seen this just about GPT-3 and all these large language models are able to just learn so much about our world. And we started asking the question, well, is it possible that these language models can be useful for vision? Is there ways that they, have learned about the visual world, and is there knowledge inside of them that we can leverage in order to do different computer vision tasks? And so, we thought this is a pretty interesting question because a large part of vision requires access to some knowledge about the world. And so much about the world has been described, on the web, and it's written down. That this seems like a really promising resource that we could try to capitalize on to build better computer vision systems. So this could be better vision systems for doing generalization. If there's a distribution shift, it could be about explainable, about bias. And we've been just exploring all the different ways that language models can be helpful for recognition. It's a little surprising at the same time because language models, they've never seen an image, right? They're just trained on text. So we're curious about what is the limits? How far can we push these approaches that are able to have side information from language? So probably most people are familiar with language models. Basically, what they estimate is a distribution of what a sentence is conditioned on kind of some part of the sentence. So, for example, you could input or input a condition like the school bus is, and then sample from the language model. And this is what GPT-3 says about this. So it will complete what the sentence is. It's basically doing some sort of predictive text. It's quite amazing. This is just the first sample that comes out from one of this about telling us what a school bus is. There's been another variant. Probably I think most people have seen language models, but if you're not following the details closely, there's actually another variant of these, which is where these language models are first trained on huge amounts of text and from the web. And they're fine-tuned on a different task, which is about following instructions. And all these language models have different names. The one that we've been using is called Instruct GPT-3, which is basically trained on question-answer pairs. And this allows you to actually probe these language models with concrete questions, and it'll give you an answer back. So I can ask this GPT model, what does a school bus drive on? Say A, and let it press go and have it try to complete what comes out. And it knows, right? It knows that a school bus drives on a road. So this is a little different from just doing language model because it's actually now been fine-tuned on a different task. But this has been actually a really key ingredient to unlock all these language models for using them in different places. And so we got kind of curious about this question. How much do these language models actually know about images, even though they've never seen an image before? And so it's pretty fun. You can just kind of probe these models about visual concepts and see what they say. And that was a lot. I mean, it was it kind of, I think a lot of people in computer vision, we say that, you know, that the foundations of perception should just be, you know, visual only. But there's actually a lot that language has to offer here. And it knows a lot about the world that we want our vision systems to learn that they're not learning. And the NLP community has created models that actually learn this, even though they've never seen an image. So you can ask it what color is a school bus, and it tells us school buses are typically yellow. You can ask it, does school bus have seats? It knows yes. It can ask it, how many wheels does the school bus have? And here it actually gives us a pretty nuanced answer. You know, it says usually there's four wheels, but sometimes there could be 6 or 8. You know, and so it actually knows the variation between all the school buses. So we've been interested in how can we use this ability to basically ask questions to a language model to aid in perception. So, you know, given an image here with the hen, you want to be able to recognize that this is actually a hen, that's not like something else, even though it has this spotted pattern here. There's a way we can use this ability to ask a question and get an answer back in language as a way to actually improve perception. And so, you know, this guy, I think this would be really useful. And we're going to show a bunch of experience about this where, you know, if you've seen something completely new you've never seen before, you actually could go ask these questions and go learn about what things are in order to recognize what's there. And so really what this, you know, approach is going to depend on is basically how well the language model can learn about the world. So one question that we basically found that works really well, kind of that you want to ask, you know, we're still in the early days of exploring this type of approach, but one question we found that works really well for actually aiding into perception is to just ask for what you want. And we can just ask these language models, you know, question, what are the useful features for distinguishing the school bus in a photo? You literally just ask this language model, how would I tell that there's a school bus in a photo? And with a little bit of prompt engineering, we figured out that you should then prefix the answer with, there are several useful features to tell there's a school bus in the photo. You put the dash there. This dash here on the left tends to be very important. And you click go, and it will just tell you what are all the different features that that are discriminative about a school bus. If I wanted to recognize that there's a school bus in a photo, these are the features that what GPT-3 thinks we should be looking for. And it's not bad. I mean, for someone that's never actually seen a picture of a school bus, it's pretty good. You know, it says large yellow vehicle. It should actually have the words, the pattern for the text school bus printed somewhere on the side. Usually there should be some stop sign that should deploy somewhere. There usually should be flashing lights, usually has large windows. You know, this is pretty reasonable. Of course, there's not all school buses are going to fit into this description, but kind of this is a pretty reasonable description for what a school bus looks like. You know, when we were starting out earlier in this project, we originally thought that this large yellow vehicle was going to be a failure, because we're thinking, how can all school buses be yellow? You know, is this just a bias? Turns out that in most countries, school buses are actually yellow. I actually couldn't find a country where school buses are not yellow. So if you know of one, please let us know. And so we actually could do this for all the different categories. Whatever visual category we think about, we could just automatically build what are the descriptors for that category. So we did this for all the ImageNet categories. You know, we asked it for all the 1,000 ImageNet categories. Just ask the language model to describe what makes that category. What are the features for that category? So the left is the school bus. You know, here's like what a golf ball is. It tells you it's small, round, and white. It should be a nickeled surface. It should be a small hole somewhere. Tells you even about the context, right? If you see a golf ball, probably there should be a golf tee or even a golf club nearby. It knows a lot. Like one of my favorite ones is the dam, right? For the hold back water. It actually even knows, you know, some of the affordances, right? How do you what is a dam? How do you actually recognize a dam in the world? There's a lot of variation, but the most important, feature to describe a dam is that it basically is going to hold back water. That's what a dam is, right? It basically prevents water from moving somewhere. And so this is really scalable. I mean, this is fully automatic. We can ask about in any category you can imagine. You know, here's just this more. We can ask about Granny Smith apples. It tells you it's green. We can ask about shields. It's going to tell you that what the material properties are, what the shape of they are, what parts there are. A shield usually has a handle, is what this is saying. Tells you what it's used for. I mean, a lot of the problems that we were trying to solve in computer vision are all about finding these features, finding these affordances. And it really seems that these language models, at least in language space, have learned a lot about this. And it's not just, you know, it's not just objects. It's works for any type of visual category. So we often try this for scenes, right? We can ask it to describe what makes a scene a scene. We can say, it tells us about barbershops, about pirate ships, movie theaters. As long as you have a category label, you basically can build this schema for all these object categories. And it will tell you what are the descriptors, what are the key features in language that build up that category. So we've been building an approach that tries to leverage these schema that emerge from these language models in order to aid in perception. And basically the main idea is that these language models can tell us what makes an object an object. And if we want to try to recognize that object, given an image, we just need to match that image to one of the schemas that these language models are telling us about. So on the left, for example, is going to be our hen here. We want to determine that this is a hen, not in fact a Dalmatian, even though the texture pattern here seems like it could be a Dalmatian based off the black and white spots. And so we want to figure out, well, you know, is this actually a hen, or what object this is? And the key thing we can do to make this all work is, rather than trying to, you know, a lot of times in visual recognition, we try to directly map the pixels to a category. Instead here, we're going to go back and actually try to estimate, you know, what is the relationship between this image and all these attributes, or all these descriptors. So rather than saying this is a hen, we're going to try to figure out, well, inside this image, there is a beak, there is two legs, that there is a small body. We're going to actually estimate the similarity between the image and these descriptors, rather than going directly to the category. And so we can directly build the score for this category. So we call our category C in our image X. We can directly estimate what is it's not really a probability, so we'll call it a score. What is the score that image X contains category C? And the way we write this is just going to be the sum of all of the similarities for the descriptors within the schema for C. And so this function D here, right, we're right, D of C, that is what GPT-3 tells us about that category. So if C is hen, then D is going to tell us what all the features are for the category hen. If D is Dalmatian, then D of Dalmatian will tell us all the features for Dalmatian. We're just going to sum all those up. And so what's interesting about this model is that this model is actually explainable by construction. That in order to estimate, you know, the score for whether category C is here, it has to first build up an explanation of these attributes. It's you know, there's a bottleneck in this model, is that it can't build up some black box embedding. It actually has to build up the descriptors first and estimate what all the descriptors are before it can do recognition. Okay, so this is the basic model. It's basically going to, you know, we tried a bunch of more complex things, but actually the simplest thing worked best, which is, let's just take a sum over all of the descriptors and let's normalize the number of descriptors, because some categories have more descriptors than the others. And so then the next question then is, how do you actually estimate this phi? Is there some way to get phi here, right? We need to, this is where we need to ground the description D into the image X. We need some relationship between the two modalities here. And we found that actually just using CLIP here works great. You can take any of these vision language models, they've got them very good. We actually can use that in order to align these descriptors to the image. And so I just want to show off kind of what some of the retrievals look like for these attributes. Because it's really fun. We have a huge website actually showing off all of these. And I just want to show you some of them. It's really amazing what these models can learn about the descriptors and about the attributes in an image. So here's just, if we take a beak, just any type of beak, it doesn't have to be about a hen, it can be any type of beak, right? It finds all the images that activate for a beak. Here they are. It's almost like a visual dictionary. You can think of this whole system as like a dictionary, right? We get the dictionary for the objects, and we get examples for what each description looks like. So here's for a tail, right? It does a really good job at tails, right? It's all types of tails. It's cat tails. It's gecko tails. There's shark tails here. And even things that, here's things that for ears, right? Erect ears. It does a great job. I love this example of the dog wearing the ears. And so it learns, has all this built up. All these models have discovered basically these attributes. And so we want to be able to say that, hey, this is a hen here because it's more similar to all of these attributes. It looks, like this thing here looks similar to the other beaks I've seen. This thing here looks similar to the other two legs that I've seen, right? I don't see anything about ears. There's no erect ears in this image. So probably this can't be a Dalmatian because I don't see any erect ears. So we're used to doing recognition, basically where we take an image and try to compare it directly to the category label in some embedding space. This is how most of these vision language models work today. We directly try to go to the category. The way you can think about this instead is we're actually comparing this to attributes or descriptors. So rather than directly comparing to a category, it gets compared to all the attributes that make up that category. So it's similar to prototypes. So we were experimenting with this model, right? It was pretty simple. To be honest, when Sachin, my PhD students, was working on this, first pitched the idea to me, I told him it would never work. And whenever you say that as a supervisor, it makes the students make it work really well. And I just want to show you some examples here. So here's an image. This is never, system's never seen this image before. What this whole model predicts is that this is in fact a hen. It predicts this is a hen, and then it even tells you why. It gives you the explanation for why it thinks this is a hen. So it says there's two legs. It's very confident that there's two legs. It says there's red, brown, or white feathers. There's a small body. There's a small head. Right. All these things are telling you. These descriptors have a high score, right? These are matching in this image, so you can build up confidence that this is a hen. If you give this same image to CLIP, which is one of these largest visual language models, it actually gets it wrong. It predicts this is a Dalmatian. And probably CLIP gets confused here because this is an unusual looking hen, right? This is not your standard looking hen. It actually has the pattern of a Dalmatian, right? So probably that's why CLIP gets this wrong. What's interesting about our method as well is because we build up these schemas, is we can actually tell you why we don't say that. So here's the score of in red are the scores of all the attributes for the Dalmatian category. Trying to match to this image here. And so while one of the descriptors gets a high score, which is black or liver colored spots, right? So that's true. There is black or liver colored spots in this image. All of the other ones actually have relatively low scores. It's very hard. It doesn't find erect ears. It doesn't find a tail or a muzzle inside this image. And so that's why it rules out that this is a Dalmatian. Here's just some more examples. I think this is very cool. It's so much fun to look through these results. So we call this a valley. CLIP actually gets this wrong. It probably learns some about spurious correlations. It calls this an alpine ibex. And why do we call this all this valleys? Well, because we recognize the mountains. We see a river there, right? We see a depression in the Earth's surface. Those are all the attributes that match highly. You don't need all the attributes to activate, right? Excuse me. So here's an attribute that is about V-shaped profile. We don't see a V shape in this. It actually has a low score, but that's okay, right? These attributes are not a requirement. It's just trying to describe what are the attributes you might see about this image. Yes, we have tons of these examples. For cloak, here's kind of unusual looking cloak, right? Probably haven't seen many toys with the cloak, and it's able to get this right, especially compared to clip that gets this completely wrong. I mean, clip in general does a very good job on all these tasks, but still not perfect, and it gets this wrong. Actually, something about the color makes this think this is a black widow instead. And here's another one, right? So we could say it's an airliner correctly, while clip thinks this is a bird, right? And really, the key to what's really cool about this is it tells you why. So yeah, this is basically a model that is trying to use a language model, which has never seen an image in order to do recognition. So we were honestly pretty surprised when we got state-of-the-art performance on ImageNet with this approach. This is basically comparing how well this model works on ImageNet V2, which is a distribution shift ImageNet, as well as a fine-grained dataset cub. And we compared this across many different architectures for how you actually do the grounding between the image and this descriptor. Basically, we see an average of 4% improvement compared to CLIP, basically on the ImageNet data set. And to me, I found this surprising for a couple of reasons. One is just these language models haven't seen an image, but two, usually when you have an explainable model, you have some sacrifice on your performance. So usually whenever you try to get explainable vision system, there's some compromise, right? You end up losing your task performance. And this actually shows it's a win-win-win, right? You basically can get better performance and you get explainability at the same time. So we've been experimenting with this in a couple different ways, and especially in the theme of this workshop about how do you generalize to new distributions. Here's a couple categories that we were experimenting with. So we built a classifier for wedding. We just asked GPT-3 for what makes a wedding a wedding, and it tells us, and we try to classify that. And here are some of the top detections for the wedding class, and pretty good, but does anyone know there's a bias, right? Is there some bias here? What's wrong with these detections? And so one of the problems with these detections is that it's basically a Western wedding. It only is going to detect a Western wedding. And when you dig more deeply into the model, you actually can see why this happens. Is because when you ask it to build a schema for a wedding, it tells us that the groom should be wearing a tuxedo, which is not always true, right? Not all cultures wears a tuxedo at a wedding. So it actually, it does well on Western weddings, but there's many other weddings that it doesn't do well on. And so what's really cool about these representations where it's grounded in language is that we can basically go edit the classifier. So if I can go in and say, well, no, I can directly inspect what it thinks the wedding is and change it, and I can add an or and say, or wedding is the same thing, but the person's wearing a kimono, and then it's going to start recognizing those images correctly. Or I can change it to say a dashiki too, right, and it's going to start recognizing those correctly as well. So this is just a very simple experiment we did. I don't think this model we don't think this model has solved all bias problems, and there's probably many more biases in this model. But when we focus on weddings and we can go basically reprogram the classifier, we basically can improve the performance drastically in all of these subgroups. Well, if you take a kind of standard model like CLIP, for example, it struggles across all of the subgroups, has a bias for Western weddings. We also got curious about, can we use this model to recognize completely new classes that's never seen before? Can we recognize, these classes that definitely were not in the training set at the time? And this turned out to be a pretty hard thing to do. Is how do you actually go build a truly out of distribution test set, especially with these like huge, large artificial language models that are basically trained on everything on the internet. So, how do you actually create new examples there? So what we did was we actually tried to find some events basically that happened after these models were trained. So I think if I remember right, these were trained in CLIP was trained in February 2021. So we tried to find some things that could not have been in the training set because they just were not popular yet. And so we found two things that we could add easily. One was the ever given, the ship that blocked the canal in March 2021. This is definitely not in the training set, right? This was not very well known ship until after CLIP was trained, as well as Wordle. If anyone remembers that Wordle game that also got popular after CLIP was trained. So we added some images to the ImageNet training set, and we wanted to see how well could we still recognize those categories. So first, just sanity check, just to make sure CLIP has never seen these. It does a horrible job at this. When you ask CLIP to recognize the ever given, it gets it completely wrong. It just finds random text. If you ask CLIP to find images of the Wordle game in this new test set, it also can't find, and it just finds a bunch of words instead. It's something about the tokenization. It can match the word. So what's interesting is that GPT-3 and these language models, because so much about these events have been written online, it actually can build a schema for them. And so, we can, when we ask this language for what is the ever given, it tells us, well, it actually is a ship. It tells us about the colors. It tells us what's written on it. It tells us, how to visually identify it, right? And same for the Wordle game. It basically expands these categories into these descriptors that we can use for recognition, and consequently, we can actually find these in the testing set, even though CLIP and the visual model has never seen these categories before. Okay, so I think this model is pretty interesting. There's still a couple of failures here. There's failures both on the NLP side as well as on the vision side. So here's a couple of schemas that we built that just had errors in the schema. Even though we're asking for visual things, sometimes these language models will start telling us non-visual things. So it tells us that jackfruit has a sweet and sticky taste or a strong smell. These are things we can't recognize in an image. This is an interesting one with Vespa because there's an ImageNet. Vespa is a scooter. But the language model tells us about the wasp instead. So Vespa is also a wasp. So there's some ambiguity with words, right? This is actually one of the big problems of language is words can be ambiguous. We also found some examples of where the grounding was wrong, and again goes back to language often creates ambiguity. So if you ask for the schema for jaguar, it tells you. But it describes one of the attributes is that a jaguar is a large and stocky cat. And so we found an interesting failure with this where the language models interpret stocky as a stock photo. And so this descriptor actually tends to find stock photos instead of a stocky cat, right? And so we thought this was a pretty funny failure here. And I think fixing this basically is going to require building more advanced vision language models. Okay, so I think I'm at 1 minute. I'm out of time. So yeah, just a couple of take-home points, which I think is, these language models really have a lot of knowledge about the visual world. Even when they haven't seen an image, they really have a lot about the world. And so by learning from these language models, you can think of it as like a form of imitation. You know, people have described how we interpret things interpret photos on the internet, and we can try to imitate that process. A lot of computer vision is about trying to imitate the process that people use. And basically learning from his language allows us to imitate and for visual recognition tasks. Just real fast, I want to advertise that if you want to learn more, our paper is online. It's called Visual Classification via Description from Large Language Models. All the work was done by Sachit Menon, who's a PhD student in my group. He worked very hard on this, and I think the results are very cool, really exciting. I really encourage you to check it out. And lastly, I wanted to briefly mention, you know, this is a I think this is a rapidly growing area. There's a lot of related work here. There's one paper I want to especially call out because it's a very similar idea. It came out around the same time from Sarah Pratt from University of Washington, who also explored how can prompting a language model be useful for recognition. So I think these are great two papers to go check out if you want to learn more about this. Thanks so much, everyone.
Thank you, Carl, for this fantastic talk. For everyone who's listening, you please feel free to insert or like post questions in on the ECCV platform in the Q&A section. And until I see questions popping up there, or before I look there more closely, let me ask maybe one or two more questions from my side.
Sure.
Very exciting work. Of course, no, like honestly, really interesting stuff. This seems like a bag of words model. Like when you go back, like 10 years, 20 years ago, there was like part-based models, right? And then they had like some kind of spatial relations. But this seems to me like a bag of words model with like part detectors that are learned basically from CLIP, right? I mean, is this like a rough embedding into the history of computer vision? Is this roughly correct, or?
No, yeah, that's right. It's basically a bag of words, or it's a bag of descriptors. Yeah, I guess for objects, that gets you pretty far. Yeah.
Do you think like that spatial relations between parts would kind of play an important role here, or how would you like integrate them? Or
yeah, I definitely think spatial relationships are important. I mean, I think it's just the natural next steps here, which is how do you start modeling the relationships between these descriptors, right? You should know that the beak is above the legs. So yeah.
But like, would language help us here, or is this or shall we go back to the old school models here?
Yeah, it's a good question. I don't think we need to go back to the old school models necessarily, but I think the questions they ask are the right things, which is how do you put all this structure in? And I do think these language models know a lot about the world. It's just the challenge is figuring out how to ask the question. So it does seem like these language models do know about some relationships between these attributes. We've been experimenting with some of this, but we haven't find anything concrete yet.
Okay. One question relating to the bus description. So in Germany, where I live, we don't have yellow buses. In case you're looking for an example. But what I found interesting is that it actually didn't describe the shape of the bus, which is kind of cuboid, which is typically like a cuboid, right? Which is kind of very discriminative, and I think even more common across countries. Is this?
Yeah, that's also true. Is that a lot of these descriptions are incomplete. So I think it's still, it's something we're still working on, is how can we get even more this descriptions. If you ask this model, are school buses are kind of a cuboid shape, I think it would probably say yes. I think it knows that. It's just how to get that information out. And one even natural next step, which we didn't explore yet, is more of a hierarchy here, right? Maybe a vehicle has this cuboid information encoded in it, and so if you were to ask it, well, what makes a vehicle a vehicle? And it will tell you, and you can keep recursively expanding those attributes. Yeah, that's one thing I like about this work a lot, is I think it opens up many more avenues of investigation than it closes.
Interesting. Any other question from the audience? I have more questions on my side, but let me first maybe. So, okay, I see one question, several questions, okay. Is a lot of data annotation effort needed for your method? I guess, or like, I let you answer.
Yeah. No, great question. No, the answer is no. That's one thing I love about it. There's basically no data annotation, because kind of language models are doing the annotation for us. So that's what makes all this possible, is that people have talked about this on the internet, and they've annotated it for us basically, and we can just query it from a language model to get all these schema.
Which is actually also like a type of data annotation, right? It's just like we can source it from the internet, but actually people have annotated images on the internet with text.
That's right. That's right. Yeah.
Okay. Any questions from people in the Zoom? If not, I have one more. So what about visual recognition by drawing?
Right.
So now that we have those large generative image models that can generate lots of really nice data, and they have language embedded. We can prompt them, and they generate interesting images that they probably have never seen before. Is there anything?
Yeah, no, I think it's a really interesting idea. I do think we're entering this era where these large models have gotten pretty good, and there's a lot of interesting work at combining them. So this is combining, both language models and CLIP together, but these generative models are another class of models that can be combined, and it would be really interesting to basically leverage those. There's been some work out of Philippi Sola's group, I know, where they try to use generative models basically to generate your own training data. I think it calls data 2.0. So it'll be interesting to see how much more this can be pushed.
There is one more question about, could this enable language-guided disentanglement instead of unsupervised disentanglement? Yeah, so I mean, can this help disentangle representations, I guess is the question.
Yeah, no, that's definitely where we're trying to go with this, is that, doing supervised disentanglement is really hard. I think there's even a paper showing that theoretically it cannot be done, just because there's too many different ways to disentangle things. So that's what we're really excited about these languages. Basically, it's an explainable disentanglement of the scene or the object. So in some ways, these descriptors are just disentangled, right? Like a beak, it's finding all beaks across all different types of animals, or tail, right? Finds all different types of tails here. So,
yeah. Maybe one more question regarding the out of distribution generalization of this. Yeah. Now we are kind of depending on the CLIP model to, kind of like also work in whatever, to detect the tail in rainy weather or in winter, or so. Right. I guess there will be, yeah, out of distribution. Like, I mean, this CLIP model is, it will suffer from like out of distribution changes in some way or the other. So
that's right. That's right.
How would you?
Yeah. So this definitely. This does very well at composition. So here's an example where this was an example where these two categories are definitely at a distribution. It's never seen these categories, but it has seen compositions of the descriptors before, right? CLIP has seen enough to know about grid levels of tiles or different colors for different letters. So this model is compositional, so it can generalize new compositions. But if there's a completely new descriptor that's never seen before, that cannot be broken down, further into language, then yeah, this system would fail, just like kind of all the others.
Okay, let's, for the sake of time, stop
Thanks.
here, as we have 1 more minute for Alex's talk to start. So Carl, thanks a lot for coming, and we are looking very much forward to seeing you in the panel discussion in 1 hour and 20 minutes from now.